Okay. So we're going to talk about pack tower today. And the pack tower, it's a little bit different from trade tower, but we're going to apply a lot of the concepts and tools we have learned about trade tower to analyze a pack tower. So first thing is, the difference between a packet tower and a trade tower. Now the difference is in a trade tower, you have discrete stages in which is a tray in which the liquid stream and contact with gas stream. But in a pack tower, so you have basically the materials being packed in this column. There's no discrete stages. And when liquid flows down and gas flows up, they contact with each other kind of continuously and gradually. Right? So in this case, for a pack tower, typically, we still know the feed composition, right? We know the composition of the gas feed, and we know the composition of the liquid absorbance. We also know the gas flow rate. Now, and we know the desired separation. That is basically the composition of exceeding gas phase, right? And in order to achieve this, given the feed composition and the condition and the gas flow rate, and given the desired separation outcome, and the design problem is basically to figure out the liquid absorbent flow rate and the height of the packed column in order to achieve the designed separation outcome, right? So here it's kind of similar to trade tower. You still need to get a liquid absorbent flow rate, right? And in a trade tower, you need to get the number of equilibrium stages. But here, because we don't have discrete stages, instead you're going to compute the height of the packed column. So how do we determine the liquid absorbent flow rate? It's similar to a trade tower, and the first thing you do is to find out the minimum flow rate, right? In order to find the minimum flow rate, you first find through mass balance, you find the operating line, and through equilibrium data, you find the through k value, you can find the equilibrium line. Then the minimum absorbent flow rate is basically you can find it by crossing the operating line with the equilibrium line at 1 and plus 1. That's basically the feed composition of the gas phase. Right? Then that will give you the minimum flow rate. The second step is you can choose the actual flow rate, right? And this is something you need to consider the trade-off between the operation and the capital cost, right? Because as we discussed, the higher flow rate you have, then you have a higher operational cost. But you will have, for a trade tower, you will have less, equilibrium stages. That means less capital cost. And for a packed tower, you will have less packed height. Again, that means less capital cost. Okay. So then the second thing is to find the height of the packed column, right? So here, we're going to still apply the equilibrium stage concept to do this, right? Even though there's no equilibrium stage here. But as we did in the trade tower, this equilibrium stage concept is very useful. It can greatly simplify the whole analysis, right? So then the whole idea is that even though we don't have discrete, even though we don't have discrete stage, then there will be certain, height of the pack tower. They will achieve similar separation effect compared to a discrete tree, right? Then the equivalent height of that, region is called a theoretical plate, and its height is called height equivalent of a theoretical plate, HETP. Okay. And then with HETP, the packed height can be determined basically by multiplying here. HTP is the ratio of the total packed height divided by the number of equivalent equilibrium stages, right? If you know the HETP, and if you know the number of equivalent equilibrium stages, then you can compute the packed height by just multiplying HETP with NT. Okay. Then now the question is just to find out NT and HTP. Then we can find out LT. Okay. So there are two ways you can get HETP. The one way is through experiment, right? basically in experiment, you can design and make an actual packed tower. Then you know the LT, right? Then you can do a theoretical analysis and figure out the number of equilibrium, equivalent equilibrium stages NT. Then you can compute the HETP for that type of packing material. Then that information can be extended to other, design of packed towers. It can also be calculated theoretically based on mass transfer coefficient, which is something we will talk about later. Okay, so now let's look at an example. So here, this is the example we basically look at in the trade tower design. So in the trade tower case, in this case, we're trying to recover alcohol from a CO2-rich vapor, right? And in a trade tower, it turns out we need 6.1 stages, right, in order to achieve the desired separation outcome. Now, if we are trying to do this with a packed tower, then first of all, depending on the type of packing, the pack height may differ, right? For a 1.5-inch metal pour ring that has a look of this, and the HETP of this type of packing is known, which is 2.25 feet. Then the total pack height is going to be we need 6.1 stages, right? 6.1 multiplied by this HETP that gives us 13.7 feet. Okay. And depending on the type of packing, HETP may be different, right? Then you may only need a less packed height in order to achieve the same separation outcome. So here, for different packing material, they could have a different HETP. The lower HETP a material have means it can provide better mass transfer between the liquid absorbent and the gas phase. Then you need less total packed height to achieve the same separation outcome, right? And typically that means this packing material is more expensive. Then next thing is we can also get HETP based on mass transfer analysis. Now, what's the rationale? How do we do that? So here the idea is, in the trade tower, we just assume equilibrium at each stage, right? In a packed tower, there will be certain height of the packed materials to achieve the same mass transfer effect, right? We just need to, and in order to find out how thick the thickness of the packed material, we just need to analyze the mass transfer between the liquid absorbents and the gas phase in a packed tower. And that way, if we can link the mass transfer coefficient with an equivalent height, we can find HETP. So before we do that, we need to kind of revisit the two film theory first, because in the packed tower, we have a liquid absorbent coming down, we have a gas phase going up, right? Then they will have interface, and the mass transfer will happen at that interface. So let's say if we have a gas phase with partial pressure, PA, and we have a liquid phase with concentration, CA, then in an idealized picture, there will be a gas film in the gas side and a liquid film in the liquid side, right? And the interface is at equilibrium, and then the solid will transfer from the gas phase into the liquid phase, right? Driven by the partial pressure gradient here in the gas film, in the gas phase, and the liquid film concentration in the liquid side, right? And if we assume there's no reaction, and at a steady state, the solute flux across the gas film will equal to that of the flux across the liquid film, then we can write down these equations. The gas phase flux proportional to the gas phase mass transfer coefficient and the driving force, that's the difference of partial pressure. Similarly, the liquid phase flux, and then we have phase equilibrium at phase boundary, right? Then we have shown that you can basically combine these three equations and condense them into one equation in which we have the total flux equals to a mass transfer coefficient, right? In this case, this mass transfer coefficient is a weighted mass transfer coefficient that has information of the mass transfer resistance in the pressure in the gas phase and the mass transfer resistance in the liquid phase, right? Then we have a total driving force here. So that's going to be the difference between the concentration in the liquid bulk and a fictitious concentration in the gas phase, right? So here, the way to understand this CA star is that, in order to compute the flux, we need to have a mass transfer coefficient, and we need to have a driving force, right? And the driving force here is some type of concentration difference. So if we use so then in the liquid phase, we know the bulk concentration, but in the vapor phase, right? So the driving force is some type of composition difference between the gas phase and liquid phase, right? Here we pick concentration to denote the composition, but in the gas phase, we cannot directly subtract, CAB from PAB, right? Because they have different units. You cannot do that. So somehow we can use Henry's law here to convert PAB to a fictitious concentration, right? Just convert. So it has the concentration unit. Then that way we can calculate this difference, right? And that will be your driving force. So I think this is not the latest version of my slides. There's a typo there. Let me pull it out. Okay. Okay, this should be the latest version. Okay. Okay. So I mean, if you are checking the Professor Sutherland's slides, there will be small mistakes here. Make sure you look at my slide. So but this is a two-film theory, right? So we can relate the mass transfer flux with the driving force. That is going to be the kind of composition difference between the gas phase and the liquid phase. Now we are trying to apply the two-film theory to solve the problem for our packed tower, right? So we can write down the mass transfer flux. Here I'm using J, right? That's different from the previous slide, but it's still the mass transfer flux. And here we use Y, that's the mole fraction, to denote the composition in the gas phase instead of the partial pressure in the two-film theory, right? We can still write down the total flux is proportional to the mass transfer coefficient multiplied by the mole fraction difference here. But now for packed tower, we need to know the total flow, right? That requires us to multiply the flux with the total surface area between the liquid and the vapor phase. And that's something we typically don't know. So to solve this problem, we define a R, that's a kind of like a mass transfer rate per unit volume, right? So the unit is mole per second per meter cube, right? Instead of meter square, because for flux, we have mole per meter square per second. And to do that, we just need to multiply and in this way, we can compute the total mass transfer, amount of mass transfer by multiplying R with the volume of your packed tower, right? That's the convenience. But in order to get this, we have to multiply J with some type of number that converts surface area to volume. And physically, this is the surface area between the surface area of your packing materials per unit volume of the packing, which is a parameter of your packing material that can be measured, right? So you just multiply A with J, then that can convert the mass transfer flux J to a mass transfer rate, right? Which is the amount of moles transferred per second per volume in your packed tower. Then we can write it down in terms of the driving force in the gas phase and the liquid phase. Okay. Then you can just rearrange this equation. You can write down y, as a function of the this. Here we have Kxa, that's a mass transfer coefficient in the liquid phase, and Kya, that's a gas transfer coefficient in the vapor phase, right? Or another way, 1 over Kya is the mass transfer resistance in the vapor phase, and 1 over Kxa is the mass transfer resistance in the liquid phase. Okay, so this ratio is relative resistance of mass transfer between the two phases. And we can also further simplify this by using the overall mass transfer approach. So in this way, we can write down the R, mass transfer rate, to be a function of the overall mass transfer coefficient multiplied by A, multiplied by the overall driving force. That's 1 minus YA, right? So when we write down the equation in this formula, we're using the gas phase composition as a driving force, right? Then Y here is basically the fictitious gas phase composition in the liquid phase, right? We are converting the liquid phase composition to a fictitious gas phase composition by applying the equilibrium constraint. Okay. And you can compute the overall mass transfer coefficient with the equation here. Notably here, we use K instead of H, right, as an equilibrium constraint, because here we are using mole fractions in the liquid phase and the gas phase to denote the composition. So that's why we use K value as an equilibrium constraint. But in the previous case, in the gas phase, we were using partial pressure to denote the composition in the gas phase. So that's why we use Henry's constant. Okay. Now we can find the equilibrium height. We call HOG, height of a gas transfer unit. To do that, like I said, now we know how to analyze the mass transfer between the gas and liquid phase. Let's just look at the packed tower. And if we look at the packed tower, if we define a kind of small control volume in the infinitesimal thickness in the packed volume, here we can do mass balance in this small region, right? So the change in the gas phase composition is the what Vy, that's the solute flowing out, minus V times Y plus dy. That's the solute flowing into this region. We can also compute the transfer to the solute being transferred into the liquid phase, right? Applying the mass transfer equation we just derived. So the mass transfer rate is going to be proportional to the overall mass transfer coefficient multiplied by the surface area, then the driving force, then the volume of this control volume, which is S, that's the cross-sectional area multiplied by the thickness, of this small control volume. Okay, then the change in the gas phase should be equal to the amount of solute being transferred to the liquid phase. So we can write down the difference here is minus Vdy equals this, right? Now we have a differential equations with dy and the DL as the variable to be integrated. Now we can do integration. So basically, we remove all the terms that's relevant to y to the right side, right? To this side. So you move like y minus y star to one side, and you move all the other terms to the other side. So we have one dy over y minus y star in one side, and on the left side here we have dl. Then we have kya as and v is divided, in this term. That will go there. Okay. So for K, A, and S, they are the geometry kind of properties of your packed tower and your packing material. And V is the vapor flow rate that's given, which is constant. And Ky is overall mass transfer coefficient. That's dependent on the key value, as well as the mass transfer coefficients in the liquid and the vapor phase, which is also constant, given if the liquid phase and the gas phase are given. Okay. Then this is a constant, so you can take it out. Then we can do this integral, right, from the bottom to the top of the column. That will give you an equation like this, where we have this integration. This integral give you LT, right? Then you divide this term to the right hand side. So you will have V divided by KYAS multiplied by this integral. Now, if we look at this equation, we notice that this term has no unit, right? Because it's y divided by y. So it's unitless, right? And the physical meaning is the number of gas transfer units, no. And this term will give you a parameter that has the unit of length, right? So then the physical meaning of this is the height of a gas transfer unit, HOG. Okay. Then for a constant key value and a linear operating line, right? This we'll talk about this later. For a linear operating line, when you have a dilute solid, you have a linear operating line. You can compute the integral of this term and to be a function of A and the y in, x in, and y out. Right? A here is basically L over kVA. That's the basically, as we will show later, this is the ratio of the operating line, the slope of the operating line versus the slope of the equilibrium line, right? Then at one particular case, when A is 1, when this term equals 1, that means your operating line is parallel with your equilibrium line. Then HETP is just equal to HOG, and the number of equilibrium stages just equivalent to just equal to NOG, right? So this is how we make connections between the HETP with the mass transfer, just connecting the HETP with mass balance and the mass transfer. Yes.
Just be clear, so the V stands for volume, not the vapor phase flow rate.
V is the vapor phase flow rate, the total flow rate.
Not the volume.
Not volume. Yeah, it's a flow rate. So S here is the cross-sectional area. V is the the vapor phase flow rate, right? So L is the liquid phase flow rate. But more generally, so as we just said, in these two equations only apply when A is 1, right? So that HETP just equals HOG, right? And HOG can be computed if you know the vapor flow rate and the geometry of your pack tower and the mass transfer coefficient, right? You can compute HOG, you can compute HETP. But more generally, HETP is a function of HOG, and it's also dependent on the A value. That's the ratio of the liquid phase flow rate and the vapor phase flow rate and the key value, right? right? Similarly, the number of equilibrium stages is also a function of nog and A. And typically there will be three scenarios. When your operating line is parallel to your equilibrium curve, they are the same. The nog is equal to number of equilibrium is equal to NT, and hog is equal to HETP, right? And then if your operating line has a higher slope than your larger slope than your equilibrium curve, you will have nog to be larger than NT. And if you have an operating line that has a lower slope, smaller slope than the equilibrium curve, you'll have nog to be smaller than NT. Now let's look at one example. How do we apply the concepts we just learned to compute the required packed height? So here, it's the same problem as example 6.1, in which we are trying to design a absorption column to recover ethanol from a gas phase, right, with CO2 as a carrier gas, right? And we've done this with Trade Tower, right? And it turns out we need 6.1 stages in order to achieve the desired separation outcome. Now let's say what would happen if we are trying to do this whole separation with a packed tower. Now what is the required packed height? Okay, so we know the composition of the feed, of the liquid feed and the gas feed, and we also know the desired output separation outcome, and we have the vapor flow rate, right? So to do this, in order to get the required packed height, we need to know the hog and nog, right? Here in this problem, hog is given, we just need to find out nog, and nog is basically dependent on A and Y in, X in, Y out, X in, right? So X in, Y in, and Y out are known in this problem, okay? And we just need to find an A, which is the ratio between L and KV. So we know V here, right? And K is a key value, which is known if you given the temperature and the pressure. For an ideal system, key value can be computed. Then we just need to find out the liquid flow rate, right? So in the previous example, the way we find the liquid flow rate is first we find the minimum liquid flow rate, right? By first of all finding the operating line and the equilibrium line, you can find the minimum flow rate. Then you assume, hey, if I'm going to operate this absorption tower at 50% more than the minimum flow rate, right? Then you have a liquid flow rate. Then you have A, right? Then you can compute LT. Right? This is what we can do here, right? Compute Y out, then you can compute A based on L, K, and V. Then you can compute nog, and turns out you need 7.5 transfer units. Then you can just compute the total packed height by multiplying the 7.5 transfer unit with the hog, right, which is 2.0 feet for this case. That gives you a 15 feet of total packed height. Now let's look at another example. So in this example, we have a mixture of ethylene oxide in an inert gas going into this column. So we use water as the kind of liquid absorbent to strip ethylene oxide from inert gas. We know the width of the absorption tower, right? And we know what type of packing we are using.